All right, welcome back, everybody. Learning is a hobby here. I finally want to get around to posting the solutions for section 3.3 in Terrence Tao's Analysis One book. So I was able to finally get around to writing up the solutions last night. So anyway, here it is. So we'll be able to move on to section 3.4 after this. Let me bring up my solutions, and then we can get started. Okay, let's start here with 3.3.1. There's the exercise set here was kind of short. There's only, I think, like 8 problems in it. And all the problems are pretty straightforward, so we should get through them pretty quick, and then we can move on to section 3.4. Hopefully I'll be able to post that video sometime this week. But anyway, let's get to 3.3.1. So here he says, let me just move this out of the way. Okay. Show that the definition of equality in definition 3.3.8 is reflexive, symmetric, and transitive. Also verify the substitution property, which is if f and f tilde from x to y and g tilde from y to z are functions such that f equals f tilde and g equals g tilde, then g composed with f equals g tilde composed with f tilde. And then he says, as an aside here, of course, these statements are immediate from the axioms of equality in Appendix A7 applied directly to the functions in question, but the point of the exercise is to show that they can also be established by instead applying the axioms of equality to the elements of the domain and the codomain of these functions rather than to the functions themselves. All right, so let's jump into it. Here's my proof. So we'll start by showing that the definition for function equality that we have in chapter 3, section 3 is reflexive, symmetric, and transitive. So we'll start with reflexivity. So if you look at, for example, the function f from x to y, clearly the set x is equal to the set x, and y is equal to the set y. Furthermore, f of x is equal to f of x for all x and x. So the function, the function f is equal to itself for any function. So function equality is reflexive. All right, then we'll go to symmetry. So let's let f be a function from x to y and g a function from x prime to y prime, such that f equals g. Then because f equals g, that means that x has to equal x prime and y equals y prime. And f of x equals g of x for every x and x. That's the definition that we have for equality in section 3.3. Okay, then since f of x equals g of x, that means that g of x equals f of x, because we're dealing with equality of the elements of the set now. For every x in x prime, and x prime equals x, y prime equals y, by the fact that equality of sets is also an equivalence relation, that implies that g equals f. So in other words, g equals f by definition as well. So that shows that function equality is symmetric. And then lastly, we got to do transitivity. Right, let f from x to y, g from x prime to y prime, and h from x double prime to y double prime, such that f equals g and g equals h. Since equality of sets is an equivalence relation, x equals x prime and x prime equals x double prime, which implies that x equals x double prime by transitivity, and y equals y prime and y prime equals y double prime implies y equals y double prime, again by transitivity. Furthermore, for all x in the set x, f of x equals g of x. For all x in x prime, g of x equals h of x. Therefore, f of x equals h of x by transitivity of equality of numbers. For all x in x, that implies that f equals h. All right, so transitivity also holds. Okay, and then they also wanted us to show that function composition satisfies the substitution property. So let's do that in the last part here. So let f equal f tilde, g equal g tilde, and consider g composed with f, which is a function from x to z by definition. And g tilde composed with f tilde is also a function from x to z, again by definition of composition. Let x be an element of x, then g tilde composed with f tilde of x equals, by definition, g tilde evaluated at f tilde of x, which is equal to g tilde of f of x, since we said f tilde of x sorry, f tilde is equal to f. So that means that f tilde of x is equal to f of x for every x in x. So those two, that's where those two equalities follow from. And then g tilde is equal to g, so g tilde of f of x is equal to g of f of x, which is the same, by definition, the same thing as g composed with f of x, and that shows that the axiom of substitution is satisfied. Okay, that's the first problem. 3.3.2 says, just move this up a little bit. Let f from x to y and g from y to z be functions. Show that if f and g are both injective, then so is g composed with f. Similarly, show that if f and g are both surjective, then so is g composed with f. So let's do injectivity first. All right, let f and g be injective and assume that g composed with f of x equals g composed with f of x prime. Then that's the same thing as g of evaluated at f of x equals g evaluated at f of x x prime. That implies that f of x equals f of x prime, since g is injective. Also, f of x equals f of x prime implies that x equals x prime, since f is injective. Therefore, g composed with f is injective. It satisfies the definition for injectivity. Right, and then we'll do surjectivity second. So now assume FG are surjective. Then for Z in Z, there exists Y in Y such that Z equals G of Y. Also, Y in Y, sorry, also since Y is an element of Y, there's an X in X such that f of X equals Y. That just follows by surjectivity of F and G. Therefore, Z equals G of Y, which is the same thing as G of F of X, which is G composed with F of X, and that's it. Right, next problem, 3.3.3. When is the empty function into a given set X injective, surjective, or bijective? All right. So here's my solutions. Let X be a set and F be an empty function to the function X, from the empty set to the set X. Then F is injective, since it is trivial that if X, Y are elements of the empty set that are not equal, then f of x equals f of y, because there are no elements of the empty set, right? So it just follows trivially. Okay, f is never surjective if x is not the empty set, since for y in x, y is not f of x for any x in the empty set. If x is equal to the empty set, then f from the empty set to the empty set is surjective, since for any y in the empty set, there exists an x in the empty set, such that f of x equals y, in the trivial sense, meaning there are no elements. So if the codomain is also the empty set, then the function is surjective. Right, therefore, the only case in which f from the empty set to x is bijective is when x is also the empty set. That's the only case that it works. Okay, 3.3.4. In this section, we give some cancellation laws for composition. Let f from x to y, f tilde from x to y, g from y to z, and g tilde from y to z be functions. Show that if g composed with f equals g composed with f tilde, and g is injective, then f equals f tilde. So that's a kind of cancellation law for composition. Is the same statement true if g is not injective? And then also after that, they want to show that if g composed with f equals g tilde of f and f is surjective, then g equals g tilde. Again, it's a type of cancellation law for composition. And lastly, they want us to say, is the same statement true if f is not surjective? All right, so let's take them one at a time. So let let g from y to z be injective, and let g composed with f equal g composed with f tilde. Then for any x in x, g composed with f of x equals g composed with f tilde of x. That implies that g of f of x equals g of f tilde of x, but just by definition of composition. And that implies that f of x equals f tilde of x by the fact that g is injective. And that implies that f equals f tilde. Right? In general, this doesn't hold if g is not injective. For example, excuse me. For example, if g of x is x squared and f of x equals x and f tilde of x is negative x for all x and r, then for example, g composed with f of 1 is 1, which is the same thing as g composed with f of 1, but f of 1 equals 1, which is not negative 1, which is f tilde of 1. Okay, next, if f from x to y let f from x to y be surjective and assume g composed with f equals g tilde of f. Then for any y in y equals f of x for some x in r. Sorry, this should not be x in r. This should be x in x. Let me just fix that real quick. Oops, not that one. Sorry, this should be for x and x. All right, then g of y equals g composed with f of x equals g tilde of composed with f of x, which is equal to g tilde of y, right? And in general, that property doesn't hold if f is not surjective. And then I'm just giving an example here. For example, if f of x is x squared and g of x is the absolute value of x and g tilde of x is x, then g composed with f of x equals g tilde composed with f of x for all x in, again, what did I use r here? I think I was writing this up without thinking about what I was writing. Sorry, this should be x again. Sorry, let me just fix this. Okay, but g of -1 is not equal to g tilde of -1. Okay, next problem, 3.3.5. Let f from x to y and g. Oh, actually, you know what? Hang on. Let me go back up here for a second. I am choosing actual numbers here, so I guess it could have been all right to say x and r here, but whatever. It doesn't matter. Let's go back. Let's go down to 3.3.5. Let f from x to y and g from y to z be functions. Show that if g composed with f is injective, then f must be injective. Is it true that g must also be injective? Show that if g composed with f is surjective, then g must be surjective. Is it true that f must also be surjective? All right. Here's the proof. Let g composed with f be injective and assume f is not injective. Then for some x, x prime and x, where x is not x prime, f of x is equal to f of x prime. Then g composed with f of x equals g of f of x equals g of f of x prime, because we assume that they were equal, right? Equals g composed with f of x prime, which contradicts that g composed with f is injective. Therefore, f has to be injective. Right? Proof by contradiction. It is not true that g must also be injective. For example, here I'm just giving an example where that doesn't have to be the case. If g of x is x squared and f of x is the square root of x, which you can check yourself. Let g composed with f be surjective, but g is not surjective. Take z in the set z, then z equals g composed with f of x for some x and x, which implies that z equals g of f of x. And f of x equals y in y implies z equals g of y, and this contradicts that g is not surjective. So again, proof by contradiction. All right. However, it's not true that f must also be surjective. For example, and again, you can check this yourself, but I'm just giving a counter example here. For example, g of x equals 10x and f of x equals absolute value of x. So in that case, it would fail. Okay, 3.3.6, let f from x to y be a bijective function, and let f inverse from y to x be its inverse. Verify the cancellation laws. F inverse of f of x equals x for all x and x, and f inverse of y equals y for all y and y. Conclude that f inverse is also invertible and has f as its inverse. And then he just says, as an aside, that would mean that f inverse is f by the definition. All right, so here's my proof. Let x be an element of the set x, and there's a y and y such that f of x equals y. Since f is a bijection, then x equals f inverse of y equals f inverse of f of x, because y equals f of x, right? And then second part, let y be an element of y, then y equals f of x for some x in x, because f is a bijection, right? It just follows from surjectivity. then x equals f inverse of y implies y equals f of x equals f of f inverse of y, and that's it. So that shows the cancellation. Right. Second to last problem, 3.3.7. Let f from x to y and g from y to z be functions. Show that if f and g are bijective, then so is g composed with f, and we have g composed with f inverse equals f inverse composed with g inverse. So here's my proof. If f and g are bijections, then so is g composed with f by exercise 3.3.2. We've already shown that. Next, let z equal g composed with f of x. Then g composed with f inverse of z is equal to x by definition, which is equal to f inverse of y for some y and y, since f is a bijection. Furthermore, y equals g inverse of z for some z and z, since g is a bijection. That implies that g composed with f inverse of z equals f inverse of y, which equals f inverse of g inverse of z, which is equal to f inverse composed with g inverse of z for all z and z, which implies the two functions are equal to each other. Okay, and last problem for this section. If x is a subset of y, let I from x to y be a function from x to y, be the inclusion map from x to y, defined by mapping x to x for all x and x. For example, I from x to y of x is equal to x. And here, the output we're considering as being an element of y rather than just an element of x for all x and x. The map I from x to x is in particular called the identity map on x. All right, and there's a bunch of parts to this one that he wants us to do. So let's do that. Show that if x is a subset of y is a subset of z, then the composition of I from y to z with I from x to y equals the inclusion from x to z. All right, so here's my proof. Let x be an element of x, then inclusion y to z composed with inclusion x to y of x is equal to inclusion y to z evaluated at inclusion x to y of x, which is equal to inclusion y to z of x, which is equal to x. And that's the same thing as inclusion x to z of x. All right, for all, for all x and x, we chose x arbitrarily. So that shows that the two functions are equal. All right, show that if f from a to b is any function, then f equals f composed with the inclusion from a to a, or the identity from a to a, equals the identity from b to b composed with f. Right, so let x be an arbitrary element of a, then f of x is equal to f composed with or evaluated at the identity from a to a of x, which is equal to f composed with the identity from a to a of x. Also, f of x is an element of b, implies that f of x equals the identity from b to b, evaluated at f of x, equals identity from b to b, composed with f of x, and the result follows by transitivity. Right, then part C, show that if f from a to b is a bijective function, then f composed with f inverse is equal to the identity from b to b, and f inverse composed with f is the identity from a to a. So here's my proof. Let b be an element of b, then there's an a in a such that b equals f of a, which is equal to f of f inverse of b, which is equal to the identity from b to b of b. Also, right, because a is equal to f inverse of b. It just shows that those two functions are equal for any value of b. All right, same thing holds for the other composition. The identity on a composed with evaluated at a is equal to a, which is equal to f inverse of b equals f inverse of f of a, and that shows that the two functions are equal to each other for any a in a. All right, then part D, show that if x and y are disjoint sets, and f from x to z and g from y to z are functions, then there is a unique function h from x union y to z, such that h composed with the inclusion from x to x union y equals f, and h composed with the inclusion y to x union y equals g. So here's my proof. So clearly, the way that I'm defining this function h here is I'm defining it as this piecewise function. So h of alpha is equal to f of alpha if alpha is an element of x, and g of alpha if x is an sorry, g of alpha, if alpha is an element of y, is such a function, and I just want to show that it's unique. So assume that h tilde from x union y to z is another such function, then there's two pieces of the domain, so I just did it in cases here. Case one, if alpha is an element of x, then h of alpha is equal to h composed with I, the inclusion from x to x union y of alpha, which is equal to f of x, but that's also equal to h tilde composed with I x inclusion x to x union y of alpha, which is the same thing as h tilde of alpha. So for any alpha and x, the two functions are equal. And then case two, if alpha is in y, then h of alpha is h composed with sorry, I'm getting tongue-tied here. H composed with the inclusion from y to x union y of x equals g of alpha, which is the same thing as h tilde composed with the inclusion from y to x union y of alpha, which is h tilde of alpha. So again, for any alpha and y, the two function values are the same. Therefore, for any value alpha in the domain of h and h prime and h tilde, the functions agree. So the two functions are actually the same. So h is a unique function, meaning that there's only one of them. Okay, and then last part here, part E, show that the hypothesis that x and y are disjoint can be dropped in D if one adds the additional hypothesis that f of x equals g of x for all x in x intersect y. And I didn't go through the full thing here, but I just gave you the function, and then you could do it yourself. It's pretty much a repetition of the argument that we just did. So here instead, what you do is you choose h of alpha to be the piecewise function that gives you f alpha if alpha is an x, and g of alpha if alpha is an y minus x. And you can show that uniqueness by a similar argument to the one that I just did. So I just didn't bother to do it again because it's the same type of thing. And that's it. That's all the exercises for section 3.3. So let me stop the screen share. All right, so the next section that we're going to do here is 3.4, which is on images and inverse images. So we're halfway through chapter 3, so there's 3 more sections to do in here, and then we can move on to the next chapter. It's been taking me a while just because this last semester was at least at the very end was taking up a lot of my time. So, but now that it's a summer session, I have a little bit more time to work with, so I should be able to get through chapter 3, and hopefully, actually, we can get through not only chapter 4 and 5 here, but also get through the Dedekind cut construction of the real numbers in Spivak before the summer is over. So I'll see you guys in the next one. Also, just as an announcement, I'm going to be posting my my June vlog pretty soon too, so keep an eye out for that. Until that time, I'll see you guys in the next one, and keep learning.